Now let us go to the third topic, thermodynamic properties. Okay, so this is again the basic building blocks of the subject. So based on this, we'll build upon another advanced topics. Okay, so in the syllabus we have, these are the key points. Sorry, we'll talk about pressure, volume, and temperature. We'll talk about zeroth laws of thermodynamics. So you must have heard first or second, but here we also have a zeroth law. Then we'll see what are the different techniques which are used for temperature measurements. We'll also talk about pressure measurements, and we'll see different temperature scales. So this is what we have in your syllabus for this particular chapter. Moving on, let us see how we define pressure. Okay, so pressure we generally defined as normal force exerted per unit area by a fluid. Okay, so we can say P is equal to F by A, right? So this is, I think you must have studied in high school physics. And when we talk about pressure at a point, we say that pressure for a area which is going to zero. So then that we define as pressure as a point. Generally, we talk about pressure on a piston. Then we say pressure is the total force exerted by the gas on the piston divided by area of the piston. Okay, and there are different units in which we measure pressure. One of them is SI unit is Pascal. Pascal is 1 Newton per meter square. We can also talk about pressure in terms of atmosphere. So 1 atmosphere is 101.325 kilopascal or 1.01 into 10 to the power 5 Pascal. So these are some of the common units. We have other CGS units also, but we will generally use this. Okay, atmosphere or Pascal. Now there are different definitions of pressure depending on how you are measuring or how it varies as compared to your normal atmospheric pressure. Okay, so absolute pressure we define as the actual pressure. Okay, at any given position, which is measured related to absolute vacuum. Okay, this is called absolute pressure. This definitions will be clear in a moment. So let me just go through. There are 2-3 definitions. Then we'll talk about them separately. So this is absolute pressure, which is relative to absolute vacuum. Now there is something called gauge pressure. Okay, so this is the difference between absolute pressure and local atmospheric pressure. So for example, if I say that there is a system which has 5 bar gauge pressure, it means that it has 5 bar higher than atmospheric. Okay, atmosphere is 1 bar, so your total absolute pressure will be 5 plus 1 6. Okay, so this is called gauge pressure, and it is calculated like this: absolute minus what is atmospheric pressure. Similarly, we define vacuum pressure. So vacuum pressure can be understood as difference between local atmospheric and absolute pressure. So this refers generally when you have lower pressure than the atmospheric. Okay, so P vacuum is P atmosphere minus absolute. This gauge is absolute minus atmosphere, while the vacuum is reverse, it is atmosphere minus absolute. Okay, let us have a look on this on a diagram. So let us say that this black line is absolute vacuum. Okay, there is no air pressure here. P is equal to 0. Now this dotted line shows atmospheric pressure. So if we have a system which has higher pressure than atmospheric, then we'll talk about gauge pressure. Gauge is whatever is higher than atmospheric. So from here to here is gauge pressure. This will be an absolute pressure. Now if you have lower than atmospheric, then we'll talk about P vacuum, whatever is lower than atmospheric. Is this clear to everyone?
Yes, sir.
Fine. Let us move on. So there are some basic definitions. Now let us see how pressure varies with height. So let us say this is a liquid pool or some tank, and this is the z direction, is the vertical direction. Now this is how the pressure will keep on increasing as we go down. Okay, so pressure of a fluid at rest increases with depth. We can say that dP by dz is equal to minus rho g. Okay, so pressure will increase as we go down. So this is opposite of the z direction. That's why we use minus. Or we can say that if I want to integrate between 2 points, that will give me delta P. So if I have 2 points here and here, I can say delta P will be equal to integration of minus rho g dz. You can take it in the RHS, you can take dz in RHS and integrate. That will give you delta P between 2 points. Okay, so strictly speaking, this is valid for both liquid and gases, but generally when we talk about gases, we say that the density is much lower, or let us say negligible. So generally we talk about hydrostatic pressure for liquids only because they have sufficient or appreciable density. But
Sir,
this, yes,
sir, screen is not visible.
how is that possible?
Sir, it
Once,
is visible.
I didn't understand the last point, sir.
okay, so anyway, I think if most of you are seeing, the video is also getting recorded. You can have a look. I hope it is visible now. You might be
Yes,
having
sir.
a poor connection. Fine. Anyone, someone was asking question on the last point.
Yes, sir.
What was your question?
I didn't understand it, sir.
So basically, what we are showing in this slide is that if you go along the height, okay. So let us say this is a tank where I have stored water. So if you go to more depth, the pressure will keep on increasing. Okay. So mathematically we say that dP by dz, how pressure varies with z direction is minus rho into g. Okay, why minus is here is because z is going upwards, p is increasing downwards. Okay, so g vector will be downwards, z will be upwards. So that's why we have a minus. So this is how pressure varies with depth for a static fluid at rest. Now, if I want to find what is the pressure difference between 2 points, okay, let us say these are my 2 points, point 1 and point 2. Okay, I want to find what is the delta P between these 2 points. What I will do is I will integrate this number, this factor. I will just take dz on this side. So we'll have rho g into dz. I will integrate it between point 1 and point 2. That will give me delta P. What is the pressure difference between point 1 and point 2? Is this clear now?
Sir, you just said now that hydrostatic band density one part, sir. I couldn't hear that.
Okay, so hydrostatic means when we talk about the fluid at rest. Just now what I explained, is this clear? How pressure varies with height.
Yes, sir, this is clear, but you were elaborating it some way. The hydrostatic density. What I didn't understand, sir.
Okay, so basically when we talk about this equation, this is strictly speaking applicable to both gases and liquids. Okay, if you have a gas also, you should do this, but generally gases have low density. Okay, so we don't take it appreciable. We just generally talk about when we talk about static pressure, we generally have liquid as the fluid. Okay, we talk about hydrostatic pressure exerted by a liquid. Gas delta P will not be that much. That's what I said. Okay, anyway, we will see some examples, so it might be more clear. So let us. So this is what I was talking about. So
So
you take
how we get dp by dz is equals to minus rho into g?
this is we know. So basically, what will happen is that we have, let us say, stacks of liquid. Okay, layers of liquid. So that is basically you are talking about the gravitational pull. So that liquid stack will have some mass, right? That force will be added here. If you take, let us say, one small mass here. Okay. So what are the forces acting on this fluid particle? So it will, if you take a level like this much mass of fluid is above this particle, right? This much mass is above this fluid particle. So it has to support that weight of that fluid. What will be the weight of this fluid? Rho g into this, whatever height is there. or let us take this case. So we have point 1 and point 2. Okay. So I want to calculate what are the, let us say I draw a free body diagram of a fluid particle at point 2. Are you following me?
Yes, sir.
Okay, so we have, let us say, a beaker or any other container. I have water filled in it to keep it simple. At point 2, I take a small fluid particle and draw the free body diagram. So what are the forces acting on it? Let us talk about vertical forces. So there will be some normal force that is supporting it, okay, from the bottom, and from the top it has to sustain the weight of all the fluid mass that is on top of this, all this height h. So or let us say if you talk about this column only, we'll say whatever fluid mass is above that particle, that mass is supported by this particle, right? This column of fluid. So it will have mass will be rho density into g into whatever height is there. Okay, per unit area, if you talk per unit area, this will be the mass of this column. Do we agree on that?
Yes, sir.
Yes, sir.
So that will be the pressure. That will give you the pressure. So force per unit area will give you pressure. That's all. Anyway, we will take several examples so that point should be clear. If not clear, you can ask at the end again. Let us go through those examples. So let us say I am talking about, let me delete it first. Yeah, let us say I'm talking about these 2 points, P1 and P2, point 1 and point 2. Okay. So how do I calculate pressure if I know pressure at point 1? I want to calculate pressure at point 2. So what I will do is when I am going down, I will add rho gh. So P1 will anyway be equal to atmospheric pressure. So P1 plus rho gh will give you P2. Now suppose if I know pressure at point 2, I want to calculate pressure at point 1. So what I will do is I will say P2, now I am going up. So P2 minus rho gh, that will be P1. So you will see numericals where you have to come down or go up. So accordingly you will calculate how the pressure is changing. Is this clear? How I have these 2 last equations?
Yes, sir. It's clear.
Fine. Moving on. So if you take a vessel of very irregular shape or size, what will happen is if you have these points A to G, they are lying on the same horizontal line, so the pressure at those points will be same. Okay, so pressure at A will be equal to G. All the pressures will be same, and they only depend on height. Okay, they do not depend on whatever shape is there, whether they are on a slope or they are a bottom. They just depend on height. They all are at, sorry, depth. H is the depth. So A to G all are at depth of H. So the pressure will be atmospheric plus rho gh. That will be the pressure there. Now H, we have mercury here. Okay, so H and I are also at the same depth, but the liquid is different. So we cannot equate them. The pressure will be different for both of them. Now let us see how we work out, how we calculate pressure for this type of configuration. Okay, let us say I have a beaker. I have 3 liquids or 3 fluids there with different densities, rho 1, rho 2, rho 3, and different heights, the height or different depths. Height of the column will be H1, H2, and H3. Okay, and this is subjected to atmospheric pressure. So this symbol actually denotes free surface. Free surface means that it is seeing the atmospheric pressure. There is no other external pressure applied. It is just subjected to atmospheric pressure. Fine. Now I want to calculate pressure at different points. Let us say I have these points A, B, C, D. I want to know what is the pressure at A, B, C, and D using what we have seen in the last slide. Okay. So PA is the simplest. PA, you can simply say that it is equal to atmospheric pressure. It is at the free surface. Now what about B? B, I can say that I will take PA and add rho GH. What is rho here? Rho 1, H is H1. So B will be PA plus rho 1 G H1. Okay, now what is PA? PA is atmospheric. So I can substitute here. I can say PB is atmospheric pressure plus rho GH of whatever the liquid is there. Is this clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Fine. So similarly, we will calculate pressure for different points. So let us say for point C. Point C will be take the pressure at point B plus rho 2 GH2. Substitute what is PB from here. P atmosphere plus this height, this rho, and then rho 2 GH2. Similarly, for point D will also be calculated using PC. You can also use PB here or PA here, whatever is known to you, plus add the rho GH. So I know, let us say I know PC, I will add rho 3 GH3. Okay. And if you substitute PC from here, this will how it will look. Similarly, if suppose I want to calculate pressure at point B and I know C for pressure at point D, so I can minus. If I go up, I will say that PB is equal to PD minus rho 3 GH3 minus rho 2 GH2. Then I will get PB. Is this clear what I have explained in this plot, in this slide?
Yes, sir.
Yes, sir.
Yes, sir.
Fine. Moving on. So let us talk about Pascal's law. So what Pascal said is that the pressure applied to any part of enclosed liquid, okay, it will be transmitted equally in all directions throughout the liquid. So by using that, this is a practical application. So you have seen this chat. So what we do is that the pressure, what pressure is applied here, let me draw it. So the pressure at this piston will be equal to the pressure at this piston. Okay. Now because we have different areas, so the force will be different. F1 will be much smaller than F2. Why? Because F2, the area is very large. Okay. So this is a direct result from Pascal's law. Now let us see something about pressure measurement. What are the different devices that we use to measure pressure? So barometer you all have heard of, I believe. So what we have there is that we have a container which is filled with mercury and there is a tube where vacuum is created. So the level of mercury rises in that tube depending on how much is the atmospheric pressure. Okay. So now let us look at the free body diagram of that liquid column, mercury column. Okay. So at the top, there is the atmospheric pressure. So P is equal to almost equal to 0. Then this column is out of height H. So we have weight of this column is rho GHA. Okay. And this is balanced from at the bottom with. So what is the force that is balancing it? Balancing the weight? Can anyone guess?
The force applied by the atmospheric pressure.
Yes. So pressure into the area of this column will be balancing this. So I can write pressure as force by divided by area. If you remove area, we'll be left with rho GH. Okay, so this is the basic principle which is used for pressure measurement in a barometer. Now one important point is that the length or cross-sectional area of the tube will not matter. Okay, it will not have any effect on the pressure measurement unless that other effects such as capillary effect are not happening. In general, the tube height or diameter will not affect your pressure measurement. That is one characteristics of a barometer. Right? Now let us talk about U-tube barometer. So what happens here is that let us say I have a gas filled in a tank at pressure A. It could be a gas, it could be a liquid. It is at a particular pressure P. So I want to measure this pressure P. So I get a device where we have a U tube. Okay, so this is basically made of glass, and we fill some liquid here with density rho. Okay, now what will happen is, because of this pressure, it pushes this liquid down. Okay, so if you leave this manometer unconnected, if this is lying separately, then these two columns will be at the same height. This will also come up, and the liquid will be of the same height. But because this is pushing from here, the liquid depresses here and it rises on this column. Okay, now we can say that if I want to calculate pressure at this point P, so what it will be? Pressure will be, if you equate, let us say this, let me draw it for you. So this is where I want to calculate pressure. This will be the pressure at which is equal to inside this box. Okay, so I can say that pressure at this point will be equal to this point. Okay, let me get some other color. So pressure at this point, they are lying on the same level. So pressure should be same. Otherwise, this column will be displaced. Okay. So if I say I want to calculate pressure for this, I can calculate pressure here also. So I'll say pressure here is P atmosphere plus whatever is the liquid column height, rho into GH. So this will give me the pressure inside the box. Is this clear to everyone? If anyone is posting any message, I'm not able to see. So either you speak up, or at the end of this class, then you can ask a question. So this is one of the simplest device which we use for pressure measurement, U-tube manometer. Okay. Now there are two different types. One is this. This is called straight U-tube. We can also have inclined U-tube. Okay. So instead of having this branch straight, I could also tilt this at some angle theta. Right. So as we have studied previously, that tilt will not matter. The height will be the same. Rho GH is what we are interested in. So that pressure will be measured same using this also. But what is the difference, or what is the advantage? Advantage is that we have a longer length here for the liquid column. Okay. So the height is the same, but because you tilt, so you get more length here. That length can be used to give more number of divisions. Okay. So you'll have, let me draw it quickly for you. So you'll have some scale which is marked here, right? So if you have a vertical scale, you will have less number of points. If you have an inclined, you have more number of points. So you can read little bit more precisely. It is not very different, but slightly more accurate or more easy to read than the straight U-tube. Okay, and we can say that we can replace. We can replace h in this equation by L sin theta. That's all. Any questions on this, or should we go ahead? Is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Fine. Let us move to other devices. So we can also use this manometer for measuring pressure drop in fluid flow. Okay, so let us say we have a pipe where some fluid is going on. Now we make an arrangement like this. So again we see that this column is depressed from here. So simply by looking at the image, I can say that pressure here is higher than this, because this is getting pushed, this is going up. So pressure at point A will be higher than, or pressure from this side is higher than this side. That's all we can say. Pressure at point 1 is higher than at point 2. Pressure at A will also will always be equal to P, but point 1 we have higher pressure. Okay. So let us assume that rho 1 is not negligible. So how do we calculate? How do we say what is the delta P between 1 and 2? So let us talk about A and B. rho1. Okay, so here we have this liquid rho1 which is filled for height. So it is taking an inclined path. I don't care about that. I only look for vertical height. Vertical height is from here to here is a plus h. So that is what I use in my equation. So for PA, I can say that PA is equal to P1 plus rho1 G into H plus A. So the same fluid is there with rho1, so I use H plus A. Similarly for PB, I will say that PB is equal to P2 plus rho1 into A, rho1 into GA, okay, because rho1 is up to this height only. Then we have rho2 filled with height H, rho2 GH. Is this clear to everyone how I'm doing calculation?
Yes, sir.
Yes, sir.
Fine.
Please tell us.
Okay. So I want to calculate pressure at point A. Okay. In terms of pressure at point 1 and similarly for B in terms of pressure at point 2. Okay. So let us say this is point 1. If I come down, as I explained previously, when you go up, you need to minus. If you come down, you need to add. Okay. So P1, now I am going down and this is the liquid column which is there. Now it is not straight, it is inclined, it is at some angle. That I don't care about. I only care about what is the vertical distance. Okay, vertical distance is A plus H. This is the height. It could have any shape, but I am interested in what is the height of that liquid column. So the height is A plus H and it is filled with only one liquid which is at density rho 1. So to calculate PA, I will say PA is equal to P1 plus rho 1 into GH plus A. So H plus A is the total height. Is this clear to you?
Yes, sir.
Fine. Similarly, I'll talk about PB. So PB is straight. Okay. So I can simply say take this height A and H. Now we have different liquids here. Here we have same liquid because that's why I used rho 1. Now we have rho 1 here, rho 2 here. So I'll say PB is equal to P2 plus rho 1 GA plus rho 2 GH. Simply I'm taking the height and multiplying by rho into G. Is this clear now?
Yes, sir.
Fine. Now, yes, any question is there? Okay. So, yes,
Sir, sir, sir,
yes,
this
yes.
pressure equal to rho GH can even be applied in flowing liquids.
We'll come to that. Right now, we're talking about only static fluid. Okay, so this is a fluid.
So, sir, this liquid is flowing or it is static?
So this liquid is flowing. Okay, we are talking about static pressure. So there is something called dynamic pressure. Okay, so that is more relevant for a
Okay,
flowing
sir.
fluid, but here we are only concerned with static pressure. So I am saying that static pressure at point 1 and static pressure at point 2. Fine. Okay. Now we know that pressure at point A and B will be equal. Okay, why? Because under them we have the same liquid column. So if any difference will be there, it will again be pushed. So that is not happening. So I believe that pressure at A and B are same. Okay, P is equal to PB. Now if I use these two equations, I equate them, I can get something like this. Okay. Now I want to calculate delta P, P1 minus P2. So this equation I will do some rearrangement. I'll get P1 minus P2 as this form. You can do this calculation and see there will be some cancellation. Rho 1 GH will get, no, sorry, rho 2 GH will get calculated. Sorry, rho 1 GA will get cancelled. So we'll be left with H. So that is what we see here. Fine. This is okay to everyone?
Yes, sir.
Sir.
Yes, any questions? Please ask.
Sir, there is no difference in the area. So, sir, how there is a pressure difference in this?
So because we said that there is a flowing fluid, okay. So because the fluid is moving, there will be a difference in pressure. So the fluid is moving because of some delta P. So the pressure at point 1 will be higher than point 2, then only the fluid is moving.
नहीं बट सर बाय द बर्नौली इक्वेशन मतलब उसमें तो यूज होना चाहिए ना मतलब कोई प्रेशर डिफरेंस के लिए एरिया वेरी होना चाहिए हाइट होनी चाहिए वेरी लेकिन 1 और 2 वाले पॉइंट्स में तो सेम है ना दोनों चीजें
Okay, sorry, we are referring to dynamic pressure here. So, okay, I need to actually, if I want more explanation, I need to add some more figures. So maybe next class I will talk in more detail. Is this fine?
ओके सर थैंक यू सर
So we'll take this question to the next class. For now, we can just fix that. This is the delta P we'll calculate for a flowing fluid. Is this okay? We'll come again to this. Okay. See, the problem here is that I don't have a blackboard. So I'm not able to draw or write things. So I will add those equations and then we'll explain it again. Fine. Moving on.
यस
Now let us also talk about other measurement devices. So this is commonly used pressure measurement bar. So this is what you fit in your gas chamber and you get pressure measurement. So what happens inside is that if you cut it, you will see something like this. So what happens inside is this yellow tube. What you see is this is called Borden tube. Okay. So this tube is designed in such a way that when the pressure applied increases, the length of the tube increases. Okay, so if you apply more pressure, it becomes longer. When it becomes longer, it moves this link and you see the pointer also moves. So you get a higher reading. The only thing you need to understand is that this tube is expanding in this direction. Once it gets higher pressure, it expands here. Fine. This is the basis of Borden tube, pressure measurement using Borden tube. Fine. So I have taken these images from these links. So this generally I will post links or image sources where you can get those images, or if you want to do some more reading, you want some more details, you can refer to these links. So for all my slides, I will be putting what links I have referred to, any web pages if I have referred to. Okay, so lastly we'll talk.
Sir, will this be
Yes. Yes, please repeat your question.
sir? Will this be available? Sir, will this be available for us in the laboratory?
Which one?
Can
This one?
yes, sir. This one, pressure gauge. Yes, sir.
Yeah, this is generally in any lab you will find this. So for example, in IC engine lab, I don't remember seeing this. Generally we use transducer, but this is also a very common device. Anyway, when you are physically back in the campus, I hope we'll have some of this. We can show you. In fact, this transducer I am in the process of buying. So I will have in a few months. I'll buy one transducer for my experiments. So that if you want, you can see. So generally this transducer, this is another device which converts pressure into analog or electric signal. Okay. So this is a very common pressure measurement device which is used for industrial applications. So for example, a barometer or manometer, you will not be able to get very high pressure or at high temperature. So these are the type of applications where transducer is very useful. And it is quite accurate. So this is generally used for pressure measurement. Okay. Transducer or this Borden tube. So these are the two common devices. Moving on. Now let us go to temperature. Okay.
So how transducer works?
Basically, there is a piezoelectric sensor here. That is not in your syllabus. You just have to know what are the devices that we use. So basically, there is a piezoelectric sensor which gives electric signal based on how much pressure is applied. That signal we calibrate and we use it to measure pressure. Is this fine?
Yes, sir.
I can also add some pictures. So let me look at it. Maybe next class I will also add some more pictures. What is there inside, and that will we can have a small discussion. Anyway, moving on to now temperature measurement. Okay, so temperature measurement we use zeroth laws of thermodynamics. So what the zeroth law says is that if two bodies are in thermal equilibrium with a third body, okay, they are also in equilibrium with each other, thermal equilibrium with each other. So let me explain it using a diagram. So let us say we have three different bodies A, B and C. So let's say that A is under thermal equilibrium with C. Similarly, B is also under thermal equilibrium with C. So if these two are true, then I can say that A is also under thermal equilibrium with B. Okay. So basically when we say thermal equilibrium, we mean that these two bodies are at the same temperature. Okay. And this law, zeroth law is used. This is the basis of all temperature measurement we do. Okay. So for example, I use a thermometer. I calibrate it with boiling water. I say that water boils at 100 degrees Celsius. This is the reading I am getting for 100 degrees Celsius. Now, if I take that thermometer to another body and I measure the temperature, if it shows 100 degrees Celsius, it means that it is at the same temperature as water was, as boiling water was. So I am basically making use of this zeroth law to measure temperature. Okay, is this clear or any questions on this?
Clear, sir.
Okay, so this is zeroth law. Now let us look at what are the different temperature scales available. So generally we will be referring to Kelvin scale for mostly our calculations. Other common scales are Celsius and Fahrenheit. Rankine is not so commonly used, but you should just know what are the temperature points here. Okay, you don't need to remember. Just remember the name Rankine. Okay, and basically we calibrate using some standard points. So one could be absolute zero, which is 0 Kelvin. Then we talk about ice point. Okay, basically the point where water melts at atmospheric pressure. And we also talk about steam point, which is at 100 degrees Celsius. Water boils at 100 degrees Celsius. And you have different equations where you can convert each scale from, you can obtain the different scale readings. Mostly we'll be concerned with Celsius or Kelvin. These are the standards unit, SI units for temperature measurement. Right? Moving on. Now, when we use devices to measure temperature, this is what we'll take into account. So we'll have a constant volume gas thermometer. We'll use pressure. We'll use to measure pressure to obtain temperature. Similarly, we'll have, so these are the types of devices which we use for measuring temperature. So we'll have constant volume, constant pressure, we'll have electrical resistance thermometer, we will have something called thermocouple, and mercury in glass thermometer, which we generally use in our household uses. Okay. Now, excuse me. So these are the thermometric properties which we measure. We'll see this in next slides. So when we have a constant volume thermometer, when we heat it, the volume remains constant, but what changes is pressure changes. So we can measure the pressure and then we can calculate how much temperature has changed. Similarly, we can have a constant pressure thermometer where pressure is held constant, but while heating, your volume will change. So we measure the volume. Similarly, we have electrical resistance thermometers. Okay, so this will measure the electrical resistance. Resistance of a material depends on temperature. Okay, so by measuring the change, we can also calculate what is the temperature there. Then we measure thermal EMF. We'll go to that in that slide. And mercury thermometer, you all know, we measure the length. How much that mercury has expanded in your glass thermometer. So let us look at all of this in its slides in more detail. So this is your constant volume gas thermometer. So what we have here is that volume is held constant, but we measure what is the change in pressure, and this will be your gauge pressure. Okay, this is a pressure gauge which measures. It could be a Bourdon tube or any other type of sensor. Now I don't know what temperature it is subjected to. Once I calibrate it, then I dip it into that temperature. I measure the pressure. I calculate temperature. Okay, so temperature is generally directly proportional to P reference. Is this clear to everyone?
Sir, what is the meaning of REF?
What is the please repeat?
So what is the meaning of REF? Pressure REF.
Reference pressure. So when we calibrate, we define some reference pressure. That is the PREF. That's it.
Sir, is this come with the
How
device?
can
We calculate it.
So basically your device will be calibrated. So for example, when you have a thermometer like this, so you have markings made. Similarly, that calibration will be done beforehand. Okay, so for example, if you buy this from market, you will be given the data that at this particular reference pressure, this temperature is coming. So if you are getting confused, if you are getting confused, just forget about this plot. Just focus on this. So this is a system. I heat it. Volume is held constant. PV is equal to an RT will be true. So pressure will rise. I measure the change in pressure, and using pressure measurement, I can calculate what is the change in temperature. That is how it works. So you people have any class after this? Can I go for 5 minutes more, or should we stop at 10?
So there is
yes, I go.
no class.
No class, no class.
No class.
No class. Okay.
There is no class.
Let us just finish this chapter today. I will take maybe 5-10 minutes extra. So this is constant volume gas thermometer. Similarly, we'll have constant pressure. Okay, so we have a stopper which can be moved. So once you have some volume, you heat it, that will move out. Okay, so the volume is changing, but the pressure is remain constant. Now I measure the change in this volume, and based on that, I can calculate temperature. Is it fine?
Yes, sir.
Okay.
Yes, sir.
Now let us talk about electrical resistance. So these are generally used for simple lab experiments. Okay, these are not used in much of practical application. For example, in industrial applications, we not use something like this or this. What we use is something like this: electrical resistance or thermocouples. So thermocouples will study next. Let us first talk about electrical resistance thermometers. Okay, so as I already mentioned, the resistance of any material changes with temperature. Okay, so this change can be used to measure temperature, and this is a fairly accurate technique. So what we do is basically we have a Wheatstone bridge. I believe you all have studied Wheatstone bridge in your school, right?
Yes, sir.
Yes. Any questions on this? Okay, so we have known resistances, and we measure the change in this resistance. We can have different elements. Okay, so this measuring element, I can wrap it on a coil, or I can have it on a plate. So this will be inserted to the gas which I want to measure the temperature. This probe can be inserted to the measuring volume. So this will give a change in resistance. This will give which will lead to a change in EMF or voltage that will measure, and then will tell what is the temperature. Is this clear?
Yes, sir.
Fine. Now let us talk about thermocouple. Okay, so this is one of the most popular devices. So what it has is it has a junction made by two different wires. Okay, wire type 1, A or B. So it has two junctions. One will be hot, and this is cold. This is maintained at room temperature, let's say. Now if I supply heat, or I provide a different temperature here, because of thermoelectric properties, this will generate some EMF. Okay, it will generate a voltage difference that can be measured. Okay, and this EMF will give you what is the temperature difference. Okay, so it is formed by two dissimilar electrical conductors. So generally we use platinum, nickel, different type of copper, different type of wire for type A and type B. So it produces a temperature dependent voltage. Okay, once it is subjected to some temperature, high temperature, low temperature, it gives different voltages. So that voltage can be used to measure the temperature, and this is a highly accurate technique, and this is one of the most popular technique for temperature measurements. Actually, I am also buying some thermocouple. So once you join, if you want, you can I can show you how it looks like. Any questions on
Sir,
Sir, examples of
sir,
what?
how change?
how?
And
Sir,
an example.
Sorry, your voice is breaking. Your voice is. Can you repeat the question or type it? Type your question here. We can see what you are asking about.
sir,
Your voice
how
is
the
breaking.
change in temperature creates EMF?
Okay, so we have to talk about thermoelectric effects. So there are different, let us say, Seebeck, Peltier effect. Okay, I will add that. So I need to add images for that. That is not there. I just wanted to give a brief overview. So how that happens is actually not in your syllabus, but if you are interested, we can discuss it. But I
Sir,
said, yes.
sir, is there any formula for means difference in EMF creates in different temperature?
Yes, there are formulas, but see, the point is that this is just a very introductory part in your syllabus. Okay, so we will not have any numerical based on this.
Sir,
This is,
can I have the example of wire A and wire B? Both has to be different now.
so different materials. So, for example, one is platinum, one is copper. Let's say so pure platinum or pure. I also don't know. There are like 7 8 types of thermocouples. So there is B type thermocouple, there is K type thermocouple. Okay, let me add more details. I just wanted to give a quick overview. If you are
Yes.
interested in more details, then I need to make more slides. Then maybe Wednesday we can talk about it. Is it fine?
No, sir.
Fine. Anyway, let us finish what we had for today. So this is the last slide, I believe. Thermocouple. Thermocouple. Any questions on this? More detail. We'll discuss this. I'll talk about this in the next class. Fine. Whatever I have discussed. Any questions on that? Anyone? How it works? No questions. Okay. Let us move on to the last slide. So this is the most common type of thermometer you must have seen. So basically, it works on thermal expansion. Okay. Mercury is held in this bulb. Once it gets heated, it expands, and by reading where the column lies, you can measure what is the temperature. Okay, I hope there's no questions on this. So with that, we have been to the end of this chapter, and I will stop now. Let me stop the recording.
Thank you, sir.
Thank you,
So any